Okay, it's 8 a.m. Sharp in California, and good morning to our participants from the North America, and good afternoon to TinyML experts and enthusiasts in Europe and Middle East, and good evening to TinyML experts in the Far East. My name is Evgeny Gusev. I'm from Qualcomm AI, and I will be the host of the webinar today. So before we start, I would like to acknowledge that TinyML has been growing quite a bit. We started this webcast series about 3 months ago, and the community has doubled since then. So we are about 3,000, or actually 3,000 people now, and it keeps growing every day. One thing you may have noticed, in addition to this bi-weekly TinyML Talk webcast series, we also started TinyML from the local groups. We had one from Montreal last week. There will be one coming from Phoenix next week, one from the Benelux, from Europe, and then from the Southern California. So you're going to see more and more activities happening in the TinyML, both in terms of the bi-weekly presentations and also more and more local events, and hopefully we'll have more real meetups, in-person meetups starting soon. So before we move on to the technical part, I would like to acknowledge our sponsors. The list of our sponsors also keeps growing, kind of a reflection of the community growth, and it's also a reflection of the value that TinyML offers to this community. So specifically, I would like to acknowledge H-Impulse, Maxim Integrated, Sense, and our new sponsor, Reality AI. Reality AI, it's a company that offers optimized feature discovery and very small embedded code with no open source, and it focuses on things like bill of materials optimizations, and tools also for managing data collection. It's a very, very interesting set of tools specifically for this market. And if you're interested in being one of the sponsors, there are more slots available. Please contact Betty at tinyml.org. And in addition to the annual sponsors, we have sponsors that can support specific events. So today it is my pleasure to also acknowledge H-Cortex to be our sponsors for special sponsor for today. H-Cortex, it's an international company. It's a startup. They're based in Tokyo and in Singapore, and they also offer automated tools to do co-design of hardware, software co-design for very energy efficient machine learning for IoT and edge type of applications. Thank you for your sponsorship. We are going to continue with our usual kind of bi-weekly cadence. So the next presentation will be in 2 weeks as usual, 8 a.m. Pacific time. One will be coming from the San Diego area. It's Venkat Radgat from Tiny Vision. He is going to continue talking about the low power CV. And the second one will be coming from the academia, from Professor Theocharis Theocharidis from the University of Cyprus. And it's also going to be a topic on the computer vision at low power. And our calendar is quite busy for the talks. And if you're interested in being one of the future speakers, please contact talks@tinyml.org. Is Aravind Darjan from Qualcomm AI Research. And the focus of this presentation is how TinyML helps to push the limits of computer vision. So Aravind is a staff engineer at Qualcomm AI Research, and he's been working on ultra low power computer vision. Before Qualcomm, he received his PhD from University of Texas, and he is the co-author of multiple research papers, and he has 6 US international patents granted. Okay, go ahead, Arvind.
Hello, everyone. My name is Arvind, and I'm a staff engineer at Qualcomm AI Research. So today I want to talk to you all about ultra-low power, always-on computer vision for TinyML applications. I also want to highlight some of the often battery-powered use cases that arise, some of our approaches for computer vision, as well as the product and software that we have. So what is ultra-low power, always-on computer vision? So our target was to have this sensor at 1 milliampere on a lithium-ion battery. And note that this is the entire system power I'm referring to. And why this particular number? Because most of your always-on sensors, and you can think of accelerometers in your pedometer or sensors for audio wake word detection, they use this amount of power. Additionally, we wanted a low latency with a typical frame rate of about 1 to 30 frames a second, depending on the application, as well as in our use cases, most of the time, the insight and information from computer vision is what's important and not necessarily the image itself. This is in stark contrast to a lot of the traditional computer vision applications. Also, historically, most of the image sensors take on the orders of tens of milliwatt to watts of power, while image processing itself takes on the order of hundreds of milliwatts to watts of power. You can think of the use cases enabled by always-on ultra-low power computer vision as falling into several categories. First, the sensor could be moving, and these are your smartphone or tablet use cases where the sensor is moving spatially over time. Or the sensor could be fixed, and these are your smart home, smart city, or IoT type use cases. They can also be categorized based on whether the ultra-low power sensor triggers a higher power, higher fidelity sensor, or if it's the only sensor in play that collects information or triggers an application. As an example of the former, you can think of face-based auto wake of your screen, which is context-aware. Essentially, when a face were to come into the field of view of the sensor, it could turn on the screen, or it could enable an IR sensor for iris authentication, or it could turn on the front-facing camera, for example, for face authentication. And all of this can be done without needing to touch the phone itself. You can also think of security camera type applications that could benefit from such an ultra-low power always-on sensor, where you have the sensor constantly scanning the scene, and in case a car were to drive by or a person were to walk by, you could turn on the higher power camera. For an example of the use case where this is the ultra-low power sensor is the only sensor in play that collects information, you can think of an occupancy detector in a room, which would turn on a light, for example, if it detects the presence of a person. So our sensor uses a very low power third-party, our module uses a very low power third-party sensor with a lens on the module, and this makes it very easy for customers to use. We've also designed a low power digital die that uses a low power MCU, which does some of the algorithms and computer vision aspects of it. The hardware block does most of the acceleration of computer vision algorithms to keep the power low. And when the event occurs, we wake up a higher power processor or trigger another sensor in order to get more information. The entire system is built from the ground up with privacy in mind. We do not send any images out, only metadata like bounding boxes. I want to highlight here that from the photon hitting the lens to the metadata coming out, our power is 1 milliwatt. And this is while running real-time computer vision applications like object detection, and without needing to perform any duty cycling. So here are some of the examples of use cases that we facilitate. We can detect several different classes of objects, with humans being our favorite. We have a variety of models for detecting humans with different viewpoints. As you can see here, for example, in a conference room like scenario, or where the subject is very close to the sensor, we have a half body detection model which detects the top half of the person. And this is also useful in cases where part of the body is occluded. At far distances, we have a full body detection model where you can detect even humans at distances of 60 feet. All these cases are fully accelerated by hardware, and we can keep the power low as a result. I want to stress a very important feature of our product, and that is the detection at multiple orientations. Here we have the face model running, which can detect faces at orientations of 0, 90, 270, and 180 degrees. This is fully, again, accelerated by hardware, so the user does not need to train for each individual orientation. And there's also no need to augment your data or your data set with faces rotated at these angles. You can just train with upright faces. We can also run other algorithms with the conjunction of hardware and software acceleration for example, change detection, where we can look at a scene and detect if a change has occurred and then further process that frame or the region of the image where the change has occurred. We also support detection of static and dynamic gestures. As an example of a static gesture, you can think of the rock, scissors, and paper gestures that we have in the game. And I'll show you a video of me playing rock, paper, scissors versus the computer using our sensor detecting my gestures. We can also detect dynamic gestures in the form of lightweight optical flow gestures. For example, a person moving their hand in front of the sensor, left, right, left. We also have models for detecting simple 2D markers and logos like the fiducial marker here, as well as 3D rigid bodies like toys. Such models are very easy to train and are quite compact. We can also run multiple models simultaneously on our hardware. As an example here, where we can see we have the face model running as well as the fiducial marker model running. And we are not limited by the number of objects, only by the model size.
So Arvind, there are several questions on the power. Power is 1 milliwatt at what frame rate? What is the sensor resolution? Is it the grayscale sensor? Or
yes,
RGB? There are some questions related to the power.
So very good question. So I will actually be getting to that a bit further on in the slide. But typically our frame rate, as I mentioned earlier, was between 1 to 30 frames a second. And our sensor is monochrome to answer that question as well. Okay. So, but I will highlight that subsequently. So coming back here, we also enable several retail use cases as shown on the right-hand side here. In the top right, you could have the sensor looking inwards towards a shelf, and you can detect whether a product is in stock, if it is disheveled, or if there's an obscuring product there. And in any of these cases, you can send out an alert. Also, in the bottom right, we could have the sensor looking outward and detect when a person were to come into the field of view. And then we could collect analytics like how long a person spent looking at that product. And we can do all of this keeping the privacy of the consumer in mind, which is very important. We don't send any images out, only analytics or statistics over time. So our image quality is monochrome and much lower resolution than cell phone images. And in many real world use cases like IoT, we deal with very challenging light scenarios. In spite of this, we perform very well, as can be seen here, where we have face detection and human body detection at really low light. This is achieved due to, sorry.
Okay, go ahead, Arvind, go ahead.
Oh. So this is achieved due to our proprietary exposure control algorithms, which also enable detection when the scene is very bright. As an example here, where we have the sun in full view of the sensor, but we're still able to detect the human body very clearly. And a typical camera would have completely darkened out the scene here in order to even out the exposure. We train our model and develop our algorithms to be resilient to all of these scenarios, which is, again, very different from traditional computer vision.
Yeah,
and finally,
there was a question from Brian, but I think you answered it. How does the low light work?
Right.
You answered that one. There is another question from Mike. Should we assume each pixel is essentially time difference for motion detection rather than running on static image? What is the time basis for differences, and is it flexible?
So yes, that's a good question. You can think of it that way. Motion is computed across different frames, so you can think of it in that way. Yes. So coming back, the sensor is sensitive to 850 nanometer IR, and this is very useful in no light scenarios. So in case there is no ambient LED, we could use an IR LED to illuminate the scene in order to perform detection. And note that this scenario would be power dominated by the IR LED itself and not necessarily our sensor. So again, I'd like to stop at this point and take any questions before I head to the next.
I think you answered them. Let's
great.
Continue.
Great, thank you. So how do we achieve this? So we take a different approach to solving this problem. In our case, the image itself is secondary to the information that it contains, as transmission of the image would dominate power. Additionally, in many of the use cases, privacy is very important, and doing everything locally and not transmitting any images is preferable. This is in stark contrast to a lot of the traditional computer vision applications, where image quality is very important. Color is typically 24-bit RGB, and features like autofocus and synthetic defocus like bokeh are also very important. For us, monochrome works well in most of the cases, and in some cases, even less than 8 bits is sufficient. And focus only needs to be good enough so that we can detect objects. And pixels are again only important when we're detecting very small objects or objects that are very far away. Everything else is for image quality, which we trade off for power. In TinyML applications, pretty pictures are not as important as the information that can be extracted from them. We also look at the entire system power end to end and not just the inference power. This is again in stark contrast to a lot of the traditional computer vision applications, which take the images as a given, but only do the processing. We shoot images in a lot of challenging light scenarios, as I showed earlier, which is again different from traditional computer vision, where the object or the camera would be moved away from direct sunlight, or a flash would be used in case the scene is very dark. We really cannot afford to do this from a power point of view. Power consumption and memory utilization play a critical role in the design of our algorithms. And finally, in many of our use cases, detecting the event is more important than frame level accuracy. So we also favor algorithms with adaptive compute. So what does that mean? It means our algorithms get more complex as the scene gets more complex. And likewise, these algorithms become simpler as the scene gets less complex. In IoT type use cases, most of the time, not much interesting is happening. So we can run our lightweight algorithms first and then terminate the pipeline there. We also favor algorithms with content adaptive capabilities, meaning that the closer an object looks like a human, the more compute is performed. This again is very useful in IoT type use cases when the scene is not, when not much is happening in the scene. This is in stark contrast to a lot of the traditional computer vision applications that use state-of-the-art neural networks, or sorry, more recent computer vision applications that use state-of-the-art neural networks, which take the same amount of time irrespective of the scene. We're also able to terminate our computation early in certain use cases. For example, if you were detecting multiple people in a room, we could terminate the detection and trigger the higher power sensor or turn on a light, for example, after detecting the first person, instead of detecting every single person in that frame. We also try to simplify compute. In traditional computer vision, we typically have one model which we run the image through, and then we downsample the image 5 or 10% to continue detecting at different scales. This downsampling is a lot more power than we can afford. So instead, what we do is we have multiple models that span the scale applied to an image, and then downsample the image 2x, both horizontally and vertically, in order to continue detection at the different scales. Finally, we also optimize power. We also optimize brightness to favor detection. And what this means is that our images are typically darker or have higher contrast than is generally nice to see for humans. And this is again very different from traditional computer vision, but we care more about detection and not necessarily having pretty pictures. We also optimize the system end to end. So we use a low power sensor, we optimize the IO, we move the core compute algorithms to hardware. And within that hardware, we keep memory as close as possible to the compute so that multiple blocks can run in parallel at higher throughput and lower power. So the product that we have is the QCC 112 chipset, which has been commercialized, and many of the use cases are supported at 1 milliwatt. So it features an ultra low power MCU, a streaming array processor, embedded power management, a vision accelerator, and we're able to get to this ultra low power target through circuit level innovations like custom memory, which gives us a 2x lower runtime memory as well as a 3x lower retention memory versus the standard retention power, versus the standard memory cell in the library. So at this point, I want to show you all a brief demo of our product. So I have this demo box with me. So this is running our, this has our module here, and it's powered by 3 AAA batteries. So this is running a face detector. And if you can see, the blue light indicates that it has detected my face. This yellow light here is more indicative of the frame rate. But this particular box is running at 100 frames a second. So that's far higher than the typical frame rate that we go for, but we're still able to achieve that using our product. This is a more indicative of this is again the same face model, but this is running at a much lower frame rate, and you can see the blinking of the LED that indicates that this is a lower frame rate. So this far, I've told you all about the features of our ultra low power module. And so how can you actually use it in your computer vision applications? How do you train your own models and run it on this device? So the answer to that is the AOCVS portal. So we provide a suite of easy to use training tools called the AOCVS portal, which customers can use to train models that run on our hardware. We provide several stock models like the face model and the human body models that I'd shown earlier. And we also enable users to train their own custom models using data collected from other sensors. So the data preparation tool converts the input images into a file, into a custom format that is used in our training. And it also provides data augmentation capabilities. So this is the data preparation tool highlighted here. So training is heavily accelerated, and it outputs a series of models, which the converter tool combines into a single model file that can be downloaded onto our hardware. So the tuner tool generates a set of Pareto optimal parameters and provides multiple knobs for the user to tune, to analyze, to optimize their power. And they can also run the model that was generated through the evaluator tool, which is a bit exact with hardware. So both the tuner tool and the evaluator tool are run in an offline manner, and they can be run on your Windows desktop or your Linux server. And you can see how the model does over a test data set. So note that we cannot support off-the-shelf neural networks because they cannot exploit our hardware acceleration. To summarize, training is a fairly simple process. You feed in your positive examples as well as annotations to the and negative images, which you can think of as background to the data prep tool, which then is used in training, and training outputs a model. So you can then run that model in an offline manner through tuner to find the parameters to optimize power versus true positive and false positive rates, or you can run it through a test set in evaluator to see how well it performs. So the AOCVS portal comes with a web-based UI and can be installed on a Windows system and is available for Linux in a containerized form. You can also install it on your local server or on the cloud, and you can access it through a browser off of your phone or laptop. Once you have the data and the required form, there's no need to write a single line of code in order to cycle through the entire suite. And the UI is very useful for quickly onboarding and getting up to speed, while we also have a command line interface for those who prefer it. So here I'm showcasing the evaluator tool, and all of our tools come with job history, with job tracking, where you have access to the job history, and so you can modify a job and rerun it with minimal effort. So on the right here, we have the detection results that come out after running the fiducial pattern model. And the results are the same as that which would come out of our hardware. So here you can see the 6 detections, the 6 bounding box coordinates. The set of parameters for this run was determined by tuner. So I'm just going to zoom into the slide a little bit to illustrate the curves. So tuner generates a curve of Pareto optimal parameters, which we can choose from depending upon our performance metric, and can compute trade-offs. This slide shows the tuner output for the fiducial marker detection shown in the previous slide. The 3 plots here come from the compute limit and are shown by the red, blue, and green plots. And the curve shows what happens when the compute limit is higher or lower than a certain amount. And this compute limit is a number that has a direct impact on the power and latency of the system. So a lower number results in a lower latency. And we can see that clearly at low false positive rates shown on the x-axis. By loosening the compute limit, that is allowing higher compute, we can get to a higher true positive rate. The curves are closer together here because this is the typical fiducial marker pattern, and so this is the fiducial marker pattern, which is not really indicative of a very real world application. But typically, you'll find that as you allow more compute, the accuracy will significantly increase. And we can tune these knobs on the fly without retraining and change our performance as we desire. So let me come back. And so next, I want to show you all a demo which illustrates the static gesture detection capabilities of our sensor. So here I'm playing rock, paper, scissors against the computer. So this is our sensor, and I'm performing a gesture in front of the sensor. And my gestures are shown on the right-hand side here. The computer player is just randomly choosing a gesture from either rock, paper, or scissors. And you can clearly see that the sensor is detecting my gesture really well and outputting that value. So yeah, so I just wanted to illustrate this capability. So, in conclusion, if there's anything you take away from this talk, let it be the following. So first, vision is probably the most challenging part of machine learning. And it is a very power hungry task. Two, by innovating on the system side, we've been able to get to a power target of 1 milliwatt. And this is while running real-time computer vision applications like object detection and without needing to perform any duty cycling. And finally, Qualcomm is the leader in this space. And I strongly encourage you to check out this link in order to find out more about the products and technologies that we have. You can also visit us or email us at this address to get more information. So with that, I'd like to thank you for attending, and I'll be happy to take any questions. Evgeny, sorry, you're muted.
Yeah, great presentation, Arvind. And related to this, there are two questions from the audience, like how do you get started? Where do you get the evaluation kit for QCC 112? Because some people have already applications in mind for this type of device, and they would like to learn how to get started.
Absolutely. Please send us an email at, let me just go back one slide. Yeah, please send us an email to this email address, and we'll be happy to set you up with getting our product and our tools as well.
Yeah, so there is a comment from Jonathan. He's saying, no question, just wanted to say that the rock, paper, scissors is awesome, which I don't
Oh, thank you.
There is a question from Alok on the low light condition. So he's saying under low light conditions, many objects may have a human-like silhouette. How does your object detect, how does your technology detects and identifies it? And in other words, what is the accuracy in under low light conditions?
The accuracy is actually pretty good. So yeah, it would depend, of course, on the object and your training, that you do for this. So yeah, the model plays a great role in the the false positives, and you can run your trained models through data sets that you can collect yourself, or through using the evaluator tool, and see how well your model does. So yeah, that would, I guess, be a function on the type of object you're trying to detect. But we've found that for the face at least, and human bodies in low light conditions, we don't get too many false alarms, and the detection is actually really good.
Okay, thank you. There is a question from Nick. I think you kind of partially mentioned this. Maybe you can elaborate on this a little bit more. How do you build custom detection model for the QCC 112? Let's say if someone wants to develop a use case or a model for whatever they're trying to do, how do they do it? How do they start? What is the process? What do they need to do? What do they need to have to get it? Yeah,
so yeah, definitely, so the main tool is, so you would need to get our always on computer vision toolkit in the AOCVS portal. And essentially, once you have this software, and it's an entire suite that you get, and you can you just need to collect data. As you would train any model, you need to have your positives as well as their annotations, as well as the negative samples, and you just feed it to the data prep tool. And after that, it's essentially there are a few parameters that you need to choose from, and you can actually generate a whole suite variety of models that you can then load onto the device and get. And you can also test their performance offline by running it through our tuner tool and the evaluator tool. So yeah, essentially, if you read our hardware, and I strongly encourage you to reach out to us to get started, and yeah, the software tools that we show here.
Okay, yeah, I think one question from Eric, he's asking if you can put up the slide with the part number. I think these slides will be available again on YouTube and on tinyml.org. So you should be able to do it. There is a question from Anup. He's wondering about if you can quantify this technology performance in terms of TOPS per watt for this hardware.
So I think you'll probably have to reach out to us for getting that information. But yeah, most of our we operate at as I mentioned earlier, we can even push our frame rate to 100 frames a second, and and all of our cases or most of our use cases are supported at about 1 milliwatt of power. So yeah, I think for the exact TOPS per watt number, I don't want to get into that at this point. Definitely reach out to us, and we'll be able to point you to that.
And one question from Ahad, also on the power budget, like what would have happened with the power budget if you had RGB camera, not a monochrome camera?
That's a good question. Yeah. So again, we've been trying to focus our efforts on having this ultra low power always on system. Yes, so the image sensor itself does play a role in the in the total power. And since we measure the total power, we just don't calculate the inference power. So if we have a RGB sensor, it would potentially take up a lot more power than our monochrome sensor that we have. So yeah, we'd have to see that and see if there are very ultra low power RGB image sensors available. It would be potentially possible to integrate them with our hardware.
Okay, great, thank you. There are two questions on the hardware constraints, one from Jonathan and from Yogan. So the questions are, what are the memory limitations of the sensor? I am assuming that we won't be able to compress and run YOLO on the sensor. That's one question. And a related question is, what models can be supported? Any constraints such as type of operations and model size? And I think there was a question earlier on the memory size as well. So kind of this hardware algorithm type of question, yeah.
Right. So our typical models are on the range of tens of kilobytes. So you can think of, so about 50 to 60 kilobyte models, run on our device. There's no constraint on the type of objects, if that was the question. We have, as I mentioned earlier, we have detection of, 2D markers like logos, as well as 3D rigid bodies like toys, and of course, human faces and, human bodies. And sorry, was there another question I forgot?
What kind of models be supported, and are there any constraints on operations and model size? And also the question on YOLO, can you run a compressed YOLO on this?
Potentially, I think we haven't tried that yet. That I think would be, up for detection. Would be something we need to try. Yeah, I can't answer that question at this point since we have not tried that. Yeah.
Okay, thank you, Arvind. So there is one important question from Ahad on the form factor. So what he's saying is, many implementations, for example, micro robots, might include some area limitations. How large is the sensor? How large is the current sensor? And what are the trade-offs between the image resolution and power consumption?
So our sensor has a 90-degree diagonal field of view. And the sensor itself, as I showed you earlier, is much smaller than the size of a dime. If I can get back to that slide. So yeah, here is our sensor relative to the size of a US dime coin, which is was I think would be the typical size of our sensor. And was there another question there?
No, there was also trade-offs between the image resolution and power consumption, given this small form factor.
Right. So there isn't. So our sensor itself, uses as a QVGA sensor, as you can see here, and that is also quite important for us to get to our power limit of 1 milliwatt that we're trying to reach. So definitely. And as I said, for us, detection is more important than actually having pretty pictures.
Okay. Good. I think there are several more questions. We'll probably have to take them to the forum for the sake of time, and maybe we should conclude with a comment from David. He's saying it's not a question, but he really enjoyed the retail example, which again we don't disagree. I think retail is a big market opportunity for this type of computer vision applications, and we see more and more information there. Like there are more questions coming, but I think we are like 5 minutes past. So I think we have to move on because people have other meetings to join, other activities. Thank you, Arvind. Again, we'll take these unanswered questions to the forums. Check out the forums on TinyML, and then you'll see more information there. And as I said before, the presentations and the videos will be available to all of you by tomorrow. And I think at this point, I would like to thank you, Arvind, and thank you, Tomer, for the great presentations today. Our special sponsor today is Edge Cortex. It's an international startup based in Tokyo and Singapore, and they focus on optimizing machine learning for doing co-design, hardware, software, core search engine, and it's quite unique technology for each type of applications, and they do it at very low latency and extremely energy efficient, kind of in a tiny ML fashion. Our annual sponsors are Edge Impulse, Maxim Integrated, SenseSense, and Reality AI is the new sponsor who joined last week. And for more sponsorship, please contact Betty at tinyml.org. So TinyML, the mission of Edge Impulse is really to make TinyML deployment as easy as possible. So they develop a lot of tools and techniques, and they keep adding more libraries and more features to help developers to deploy TinyML on their devices. So check out their website if you're interested in more information, and if you would like to get a free account to get started with this technology. So Maxim Integrated is a big established company. They have a lot of activities. It's a silicon and hardware company. So they do work in many different areas, but specifically to TinyML, it's sensors, low power processors, and they have AI acceleration coming soon. Also check out their website and announcements there. SenseSense, it's a startup based out of Switzerland, and it's formerly known as AI CTX, and they build ultra low power devices based on neuromorphic architecture, and it can be used for many different applications, embedded, mobile, edge devices, and so on. It's kind of inspired by nature. Reality AI, as I said, it's a new sponsor, and they go beyond the developing workflows. They do a lot of optimization, and it's effectively a next generation AI tools for productization of TinyML. They do feature detection and extremely small codes. You have a lot of sensors there, and it does a lot of automated data and collection and so on. And the key there, it's not open source type of issues there. As usual, we are going to have our next talks in 2 weeks at the same time. So we hope you're there. And at this point, thank you for your attention today. Thank you for your active participation, for questions. Thank you, our speakers, for the great presentations. I think both of them were amazing. And thank you for our sponsors. I think your support is quite important to keep this webcast going. So thank you again, and we'll see you in 2 weeks. And the local events will be happening in between. I think the TinyML Phoenix is going to be on the 28th next week, and then we'll have more local events happening in August as well, in Benelux, Southern California, Irvine area, and so on. Thank you.